Okay, so here comes to a very hard question or a very commonly asked question in the examination. So before we start the question, so let's see some concept behind it. So first of all, you will see that multiplication of matrix is very complicated. For example, if you have a matrix A, so which is called ABCD, in order to find A square, so it would be ABCD multiplied to ABCD, you need to write the matrix, the two matrices separately. And afterward, you multiply or find the next number by multiplying horizontal and to the vertically. So for example, which gives you now is equal to a squared plus bc. Similarly, you can have ab multiplied to bd, which gives you ab plus bd, etc. Well, I don't continue. So the main point you will see that a squared definitely is not just simply a squared, b squared, c squared, d squared. We don't have such a favorable result when you're talking about square because the multiplication of matrix is very complicated. But mathematicians find that there is a very important feature about some kind of special matrix, which is called diagonal matrix. The name we have mentioned before, and then now we see the importance of a diagonal matrix, which help us to simplify our calculation in some way. For example, this time if you have another matrix which is called B, like it's called A00B, and you can still work on the multiplication procedure, but yet I will tell you it carries a very favorable result, which is B squared will be A squared 0 0 B squared, B cubed the same, or coming to later on you will see that B to the power n is A to the power n 0 0 B to the power n. Now, this is the most important result talking about diagonal matrix. The result is special because it's not just only applied in 2 by 2 matrix, but for example, if C is another matrix, diagonal matrix, that means along the diagonal you have ABC, whereas the other entries they are all zeros. C to the power n also carries the same answer, which is A to the power n, B to the power n, C to the power n. For the rest of the entries, they are all zeros. Now you come to your question, when you are going to do talking about power, because you know power n, power 2 or power 3 is very common when we are doing math calculation, right? So that's why as a result, if you have a matrix called P or maybe a matrix called Q, if you want to raise it to power n, would there be a way that we can find this to the raise to the power n in a very simple way? This is the core method. So as a result, this is a process which is called diagonalization that will be introduced normally in year 1 in university, that you are going to change your matrix Q by a certain way with the help of a matrix P, in which we have a very special matrix to be considered P inverse QP in order to find Q to the power n. So in this video, we particularly address to this method, how we can make use of a matrix P to make a diagonal matrix called P inverse QP. Lastly, we want to find Q to the power n. Before we start talking about the question explicitly, a very big remark in part B would be, I see P inverse QP over there. I remember that P inverse P is equal to I. And let's see how or what's the mistake I made here. I swap Q and P, having P inverse PQ. Then that means it's IQ. I is identity, so that means it's a Q. What's the mistake I made here? Yes, that's good. The mistake I make is I swap the order of the product of QP, at which you remember multiplication we don't have the commutative law. That means you can't swap the order of A times B to B times A in general. So that's why the process here in yellow, they are totally wrong. And as a result, now we come to look at the details of how we do the calculation on this example 18. Let's start the question now. Okay, so you do remember that part B, so the construction of P inverse QP would be a process called diagonalization, in which we want to make it to be a diagonal matrix. So that's why when you do the calculation from A to B, make sure that the outcome of part B should be a diagonal matrix. That means it's in the form of AB along the diagonal and all zeros in the other entries. Now take a look in part A. Part A will be a very standard procedure on finding inverse. So let's recall inverse will be defined or calculated by 1 over determinant of P multiply the adjoint of P, in which each of them, so they carry different nature. Determinant is a scalar, a value, so that's why 1 over determinant of P is just a number. Whereas adjoint of P will be a matrix of the same size of P, that means now it's 2 by 2. So let's work out the answer. Determinant of P will be, so the direction will be 1 times 3 minus 2 times 1. So that's why it gives you the outcome called 3 minus 2, which is a 1. That's very good, a very simple number. Whereas adjoint of P, so don't forget that there is a transpose at first, negative sign in some positions, and then next you start going to work out the answer. In the first position, you cross out the row and column, and you get a 3 here. Second entry, so you add the minus sign in the beginning. It will be safer not to miss it in the end. Cross out row and column, you get a 2. So you work out the answer in a similar way on the matrix P now. Alright, and then the answer should be a 1 here and also a 1 here. After having the transpose, it goes to a 3 minus 2. Transpose means turn the row into column, and minus 1 and 1. Finally, you can get P inverse in a very quick way. Because the determinant is 1, 1 over 1 is also 1. So that means the P inverse will be directly equal to the adjoint, which gives you 3 minus 1 minus 2, 1 finally. Next, in part B, you're going to find P inverse times Q times P. So there is no fast way to get the product of 3 matrices, but you have to do the calculation one by one, carefully, step by step. So I write down P inverse Q and also P. So at first, I will multiply the first 2 matrices, which gives you, so you do it very slowly, carefully. 3 plus 4 is a 7, minus 3 plus 4 is a 1, minus 2 plus 6 is a 4, and 2 minus 4 is negative 2. So you let me double check it. Okay, the first number should be wrong. So it should be 3 minus 6 is negative 3. Okay, coming up next, so we continue. Also row multiply to column, so to get every entry of the matrix. The first one gives you a negative 1. Next is 0. 4 minus 4 is also 0. 4 minus 6 is negative 2. Okay, so if you get such a result, then hopefully it's correct because it's really a diagonal matrix. After obtaining this diagonal matrix, then we have a question. How can we use P inverse QP in order to find Q to the power n? So what's the relation between them? Because, so you just know that for diagonal matrix, which means for this one, if you raise it to power n, then it's equal to minus 1 to the power n, minus 2 to the power n, 0, 0 in this way for the outcome of the matrix. But you're just talking about P inverse QP to the power n. How it will go in order to get the answer for C? It will be talked about as follows. Right now, we just talk about P inverse QP to the power n is equal to minus 1, 0, 0, minus 2 to the power n. While for the right-hand side, so because it's diagonal matrix, so that's why you have a very favorable result by just moving in the power to the number along the diagonal. Now it comes to a question how we relate this left-hand side into Q to the power n correspondingly. If you try to, so the trick is you have to break down the left-hand side in order to read some feature or trick behind it. Because once you write it down, so you have P inverse QP. Next, you also have P inverse QP, P inverse QP, etc., etc. According to the question, they are totally power n. That means we need to write down n terms over there. Now, so you will see there's a big trick because now the brackets can be taken away, right? The brackets can be taken away because it's just a product. Now, if you take it away, then can you see that P and P inverse, they can be cancelled to each other because it's just an I. P and P inverse, they can be combined together, it gives you an I. P and P inverse and P, etc. Can you see that each of the neighbor to the brackets, then there should be a P and P inverse which comes to an I, or you can say they delete each other. In this case, what is left in the expression will be the front number, P inverse, the end number, P, and there are a lot of Q in between, right? So for how many Q there, it depends on how many terms are there. Do you agree with it? Hopefully yes, because how many brackets are there, how many terms are there? How many brackets are there, how many Q are there? So as a result, in this situation, now we can read the number of Q, there's Q to the power n. And you will see how it will go when we are talking about part C, which is our main target. Because now P inverse Q to the power n multiplied to P, which is equal to minus 1 to the power n, 0, 0, minus 2 to the power n. And then, so in order to get Q to the power n, so the next case will be how I remove P inverse and P. And now, so it comes to the last trick. In order to cancel it, it's like having P inverse cancel, P inverse cancel when we break down the power n in the, for the expression in part B. So in order to do it similarly, so I multiply P in the front and P inverse at the back. P in the front and P inverse at the back. Because now if you continue to write the brackets, is P inverse Q to the power n and P, which P inverse becomes I and they cancel each other. P inverse becomes I and they cancel each other. So that's why the right hand side becomes Q to the power n. Whereas on the right hand side, maybe I turn it in blue, P is something I know, which is 1, 1, 2, 3. The brackets is terrible, but yet it's just a number having minus 1 to the power n and minus 2 to the power n. Whereas P inverse, we've also got it. It is 3 minus 1 minus 2 and 1. And at last, it goes to a very tedious word on expanding it. The first two goes to minus 1 to the power n, negative 2 to the power n, 2 of minus 1 to the power n, and 3 times minus 2 to the power n. Okay, you let me double check the answer. Alright, next word, so we continue. So next, it goes even more bulky, 3 of minus 1 to the power n, minus 2 of negative 2 to the power n. Next one is minus 1 to the power n plus 1, and plus negative 2 to the power n. Next is 6 minus 1 to the power n, minus 6 of minus 2 to the power n. Minus 2 to the power negative 1 over power n, plus 3 times negative 2 to the power n. So very big, right? So again, you let me check the answer. So at last, it comes to the presentation of the answer. So somehow this one you may end like this, but in some books or maybe in the book, it will be in different looking. Because like the first one, A11 entry, because minus 2, they are duplicated. So that's why sometimes we will put them together, and it goes to negative 2 to the power n plus 1. An even more terrible situation would be a minus 6 carries a minus 2 as a vector. So that's why it will be put together with the brackets. Going to 6 minus 1 to the power n plus 3 negative 2 to the power n plus 1 is also okay. And then the A22 entry and negative sign can be put together with the brackets. So it may go to 2 times minus 1 to the power n plus 1 and 3 times negative 2 to the power n. So for the last one, A12 entry, and I think this one, so that's the end. Finally, so you don't need to bother too much about this kind of difference in the answer, because we are not that picky in the marking, because the main job will be whether you can apply the ways of making a diagonal matrix in order to find power n, as well as how you do the calculation in order to find Q to the power n. That means the target, the target you are finding. So here comes to the end of the question. see if it helps you